This lesson is about related rates. So you might be wondering what a related rate is. What does that mean? Well, a related rate is a rate of change of two or more related variables with respect to time. Basically, in this lesson, you're going to be using your knowledge of implicit differentiation and chain rule for taking the derivative in order to find the rate at which something is changing with respect to time. So let's practice translating some verbal statements as a related rate with respect to time. Suppose we want to translate a verbal statement into a mathematical model by first assigning some variables. If you read this first statement, the velocity of a car after traveling for 1 hour is 50 miles per hour. So we're dealing with velocity, which involves distance and time. So I'm going to start off by just assigning some variables here. Let's call x the distance, and the unit of measure here is miles. So I'll just put that in parentheses that that's our unit. And then t is time. Okay, so then how would I represent velocity? Well, velocity is simply the rate that our distance is changing over time. So dx dt. So the final translation would be that the velocity, or dx dt, is equal to 50 miles per hour when time t equals 1 hour. Okay, let's look at the second one. Water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. So we are talking about volume in this case. So let's assign a variable for volume. How about V? So if V is the volume of water in the pool, and to translate this, we would just say that the rate at which the volume is changing would be dV over dt, the rate at which the volume is changing with respect to time, is equal to 10. That's it. The rate is 10 cubic meters per hour. All right, in this last one, it says a gear is revolving at a rate of 25 revolutions per minute. A revolution is 2 pi radians. So if we first want to assign some variables here, we could go ahead and call theta our angle of revolution. And so to translate this statement, if the gear is revolving at a rate of 25 revolutions per minute, it's the rate at which the angle of revolution is changing with respect to time. So that would be the rate that the angle changes, d theta, with respect to time, dt. And in this case, that's equal to 25 revolutions. And now a single revolution we see is 2 pi. And the units here would be radians, because we're talking about radians when we're using 2 pi. So it's 25 times 2 pi radians per, and then time in this case is minutes, so radians per minute. Before we actually solve any related rates word problems, I'm going to give you some guidelines. Okay, so the first thing you want to do is draw a sketch of what's happening in the scenario. They're going to give you a word problem. You need to figure out what it is they're talking about. So draw a picture of it. Then identify the given variables and the variables to be solved for, and go ahead and label your picture with those variables. The second step is to come up with an equation that is relevant to the situation. So you want to write some type of equation relevant to the scenario in the problem. Okay, once we have an equation, that's when we get to do the fun stuff. We're going to differentiate the equation that we have using implicit differentiation with respect to time. Last but not least, once we differentiate with respect to time, we go back to our given information and we're going to simply substitute and solve for what we were looking for. All right, so now let's do a couple examples. Suppose a pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Okay, so we can sketch what's happening, right? We have a circle, and then a circle within a circle, and then a circle within that circle. right? So this pebble that was dropped in is creating this ripple effect. So this is the picture that you want to start drawing. First and foremost, I started sketching a picture of what was happening, and now I'm going to start identifying the variables that are given and the variables that we're trying to solve for. I'm given r, which stands for my radius. I also know I'm dealing with area here, so we'll go ahead and call A the area of the circle. We know t, of course, is going to be time. Now we have to translate the next part that says the radius of the outer ripple is increasing at a constant rate. So a rate, remember, is going to be the change of the radius with respect to time, so dr dt. Then translating that last part of the problem, they're asking us to find the rate that the total area of the water is changing. So the rate at which the area is changing with respect to time would be represented by dA dt. The next step, step 2, is to identify an equation. Well, the equation that we're going to use here is the area of a circle. So area equals pi times the radius squared. Now the fun part, we get to do implicit differentiation of that entire equation, all with respect to time. So the derivative of a with respect to time is simply dA dt, and now the derivative of pi r squared with respect to time would simply be pi times 2r times the derivative of r with respect to time, so dr dt. Remember, pi is just a constant there, so that can be pulled out before we differentiate. Lastly, step 4, go ahead and identify any of the given values in the problem. We know dr dt is equal to 1. That was the rate that the radius was changing. They're asking us to find the rate at which the area is changing when the radius is 4. So we're going to go ahead and substitute those values in. And when you replace dr dt with 1 and r with 4 and simplify, we're going to solve for dA dt, and we get the rate at which the area is changing is 8 pi square feet per second. Remember, since it's area, our units should be square feet. All right, example 2. Suppose air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute, so cubic indicates volume. Find the rate of change of the radius when the radius is 2 feet. So I'm going to start by sketching a balloon. It's a spherical balloon, so step 1, draw the picture just so you can visualize it, and then label all of the variables. Identify everything that we're working with. Well, we're working with the radius of the balloon, so r will be radius. We're also dealing with the rate at which the radius is changing, which would be dr dt. Since it's labeled as cubic feet per minute, I know that I'm dealing with volume, so let's call volume V, and then the rate at which the volume is changing would be dV dt. Make it easier for our step 4 later on, let's go ahead and write down what values we're given and what it is we're solving for. So we know that the rate at which the volume is changing is 4.5, and we want to find the rate at which the radius is changing when the radius of the balloon is 2. Step 2, what's the equation we're going to use? We're going to use volume of a sphere because the balloon is spherical. Volume is 4/3 pi r cubed. And if you don't remember that from geometry, don't stress out about it. They do give you those formulas on the AP exam. But now that we know that that's our formula, step 3, we're going to differentiate everything with respect to time. So the derivative of volume with respect to time would be dV dt. The derivative of the right side of the equation there with respect to time, well, 4/3 pi is really a constant, so you're just differentiating r cubed. And that would be 3r squared times dr dt. Now, last but not least, just go ahead and substitute all the values that we know and then solve for dr dt. So we know that the rate at which the volume is changing is 4.5, so we can replace dV dt with 4.5. And we know that the radius of the balloon at this moment in time is 2, so replace r with 2. And now let's figure out what the rate at which the radius is changing is at that time. So just cleaning everything up and simplifying here, we're solving for dr dt, and we end up getting 0.09 or 9 hundredths. So remember, you always need to write the proper units. This would be feet per minute. It's a rate. Every rate has to be per the unit of time. So this would be 0.09 feet per minute. That's the rate at which the radius of the balloon is changing at that time. Okay, let's do one last example. In this example, it's talking about an airplane flying on a path above a radar tracking station or above some type of building, and it gives us the altitude information and the distance of the plane from the station. So the first step, I'm going to sketch a picture. You should notice that if we're given the altitude, which is the perpendicular distance, we want to set up this right triangle here. And then I'm going to assign some variables for all of the parts of that right triangle. They already tell us that S represents the distance of the plane from the station, so hopefully you recognize that that's the hypotenuse of that right triangle. This base, that highlighted part there, would be the plane's distance, or excuse me, the distance to the altitude from the station, and we're going to call that X. So that's just the distance from the station to the altitude. That perpendicular distance is the altitude, if you remember from geometry. Okay, so then we also want to give a variable to that other base of the other leg of that triangle, and we'll just call it y. So we'll call the altitude side there y. Now you want to go ahead and set up the variable representation for the rates of change of each of these things. So ds dt would represent the rate that the distance of the plane from the station is changing. Dx dt would represent the rate of change of the distance from the station to the altitude. In other words, actually, dx dt, that rate at which x is changing, that's going to tell us the airplane's velocity at any given time. And then last but not least, we could represent dy dt, which is the rate at which the altitude is changing. But in this problem, the plane isn't changing its altitude up or down, so we're really not going to utilize that information. However, I do know that the altitude of the plane is 6 miles, so that's actually constant and unchanging, so I'm just going to replace that y with 6. That's not going to be variable at all in this case. All right, so next let's replace some other values that we know. We can replace ds dt, we know that rate, it's given to us, as negative 400 miles per hour. Negative since it's telling me it's decreasing. We also can replace dx dt with basically a question mark. That's what we're looking for. So dx dt is what we're solving for. Remember I said we're not going to use the dy dt because that's unchanging, so that's not even relevant to this problem. So now we need to move on to step 2, and we need to come up with an equation that relates all of these variables. Well, looking at the picture, I have a right triangle. So what better equation to use than Pythagorean theorem with the right triangle and the 3 sides of the right triangle? So that would be a squared plus b squared equals c squared. And so we're going to actually utilize what we have labeled in our picture with a, b, and c. So my a is x, my b is 6, and my hypotenuse c is s. So x squared plus 6 squared equals s squared is the equation that you're going to use in step 3 to differentiate. So now differentiating everything with respect to time, we get 2x dx dt plus the derivative of a constant is 0 equals 2s ds dt. And finally, in step 4, just replace all of the values that we know for x, s, and ds dt. Since we didn't know what x was equal to in that right triangle, we just simply have to use Pythagorean theorem to solve for x when s is 10. So you should get x equals 8. Substituting and solving for this, we end up getting dx dt equals negative 500. So that's actually the plane's velocity. And remember, the velocity is the derivative of position, which would make sense why it's dx dt. It's asking us for the plane's speed, though. So the speed doesn't have direction, so it wouldn't be negative. It would simply be positive 500 miles per hour. That is the speed of the airplane at that time. All right, that's it for today's lesson. With lots of practice, you will be a master of solving related rates problems in no time. Thanks for watching.